Thank you all for coming. My name is Tim Baldridge. I'm going to talk a little bit today about a language I've been working on for the past year, along with some help from some other people, called Pixie. It's actually kind of cool that about exactly a year ago, the first commit for Pixie was made. So it's in that interesting point in time for language development where it's in the middle of alpha to beta. So you can do cool things with it. You can build some cool programs, play around with it. Come and tell me that you're running your startup on it, and I'll probably call you a fool. Let's get started. So the words I use to describe Pixie today are, it'll make your computer shut off, first of all. Let's see if the screen comes back. My computer went to sleep there. Hopefully it doesn't do this a whole lot more. There we go. Okay, so the words I use to describe it is it's a small, fast, light Lisp with magical powers. And we put magical in quotes because nothing is truly magical in computing, right? It was all invented by someone in the 70s, and we're just kind of rediscovering it. But I'd like to talk about each one of these things individually, and we'll go through them a little bit. So first of all, it is small. If you compress it with gzip and download it, it's about a 2.5 meg download. When you start the REPL, it takes about 10 megabytes of RAM, which seems to be pretty small for languages today. And the startup is pretty good. It starts up in about 175 milliseconds on my laptop, and on other systems like Raspberry Pis and ARMs, it starts up a little slower, but that's to be expected. So it's small, it's also relatively fast, it's lightweight, and I use this word fast to describe it as well. And I'd like to dig into that a little bit. So I wrote, as an example today, a Mandelbrot calculation program. And to kind of frame this, I've written the same algorithm before in Java and using LLVM bytecode. And the Java version takes about 600 milliseconds to render the same algorithm. LLVM bytecode takes about 500 milliseconds. And let's see how this works with Pixie. Now to put this in mind, the Java version was statically typed using doubles. The LLVM bytecode was also using doubles, but in a bytecode format that was then compiled with their JIT. And let's run this here in Pixie. This is fully dynamic Lisp code running this, and once the JIT warms up, we're at about 743 milliseconds. So it's not slow for doing math-like things. And we can take a look at that code real quick. So here is the guts of that. And you can see we don't have any type hints. We don't have any types at all whatsoever. This is purely dynamic Lisp code. In fact, the only things we see of types at all here are the floats, and there's a call to int down here that does some conversion. And that's purely for making sure that it does the math that we want it to, truncating floats, extending ints to floats, that sort of thing. But there's no type hints at all given to the JIT. It just kind of figures it out on its own. So let's get back here. And let's go ahead and start up a REPL, because that's what we should do in any Lisp, right? Okay, so we have a REPL here on the right. Start it up. So the actual magical bits I want to talk about today really fall into these 3 or 4 categories. First of all, Pixie has what's called a tracing JIT, and that's relatively rare in programming languages, and we'll talk about that. It has some lightweight threads, or stacklets as they're called by the virtual machine, and we'll talk about that. It has excellent C interop, and I'll go over how that works as well. And it's a Lisp. I mean, I consider Lisp a magical power because I like Lisps, right? So the syntax for Pixie is quite inspired by Clojure. This is mostly because I program in Clojure for a day job, and I never really programmed in Scheme or Common Lisp, and so I prefer the Clojure syntax. So if you're unfamiliar with Lisp, it's actually pretty simple. Things in parens are function calls. The first thing in the paren is the function. So let's see here. How about I hit the right? There we go. So plus 1 and 2 returns 3. If we have x equals 42 and then we increment it, it returns 43. We have immutable collections. So here we have a hash map. A is 42, B is 1. And that works as expected. And they are immutable collections. So if we say M is one thing, and then we modify it down here in this assoc, we can print both the old and new versions of the hash map, and that works as we expect. Now, I stopped short of calling this a variant of Clojure because there are some small differences, and I kind of wanted the flexibility to change Pixie at any point because I wanted to do something a little differently for performance reasons or whatever. And one of them we can kind of see here. So if you've programmed in Clojure, you know that a function with a variable number of arguments, those arguments get handed to you as a linked list. And in Pixie, that's a little different. They get handed to us as an array. So there's going to be little things, perhaps, that you run into using Pixie that are a bit different, but I'm sure we can live with that. Okay, so Pixie is a language that has its own JIT and its own virtual machine and its own runtime, and it's built off of what is known as the RPython toolchain. So who here is familiar with PiPi, at least has heard of it before? All right, good number of people, excellent. So the developers of PiPi did an excellent thing when they started that project. And for those of you who aren't aware, PiPi is an implementation of Python in Python, which sounds like a fantastically bad idea until you actually realize what they did. And what they did was they wrote an entire tool chain for building languages in Python. So the basic idea is that you write your interpreter in this thing called RPython. And RPython is a reduced subset of Python that is fully inferred in statically typed code. So it basically takes your Python code, does a lot of crunching on it, and spits out something that has to be able to compile to C. So those are kind of the restrictions. It has a type system somewhat like you would expect in C, but it's all statically inferred. And to that code, before they translate it to C, they include a garbage collector, which is kind of a nice feature. So you start off and you write your interpreter and your compiler and your parser in this C, quasi-C Python thing, and you run it through the translator and it spits out C code that gets compiled into a C executable. Now that in and of itself is not an incredibly cool thing. I mean, if I was just wanted to build a language, I would probably just use C instead of using some mostly working tool chain. By their own admission of the developers, it mostly works, right? But there's another reason to do it this way, and that is to get a JIT. The tool chain provides tools for writing a JIT, specifically a specific type of JIT known as a tracing JIT. So to look at why we would want something like this, let's look at a piece of example code. So here's some code in Pixie that says do times x to 10,000. So this will start x at 0 and loop 9,999 times, incrementing x each time. Now the actual guts of that code looks something like this. Do times is a macro that expands to this loop. X equals 0 while x is less than 10,000, increment x, and then jump back up to the top. Okay, so what's increment? Well, increment is this tiny function that says x plus 1. All right, well, what's plus? Well, plus does a bunch of things, but one of the things it does in Pixie is called -add. Great, that doesn't help us much at all. So what is -add? Well, -add is a double polymorphic function, or a function that dispatches on the first two types of the arguments handed to it. So in this case, we're saying if we are handed an integer and an integer, then we want to call this primitive function called addInts. And the actual code behind this in Pixie is a little bit different, but we're using this as an example for today. So the problem is with a normal traditional JIT, like a method level JIT that you would find in LLVM or .NET, it's a little hard to figure out what the JIT should do with this. If it comes up to this function increment, what can it really figure out? Not a whole lot. There's not a whole lot of context here. It says you will be given something, and then you will pass that to this plus function. You know, what sort of unboxing or optimization or enhancement can it do here? There isn't a whole lot. There's not enough context. Now there are other JITs out there, such as a lot of JavaScript JITs, and Hotspot is just a really weird beast that exists somewhere in between these two classifications of method JITs and tracing JITs. In general, they also work the same way. They work by inlining, by finding ways to partially evaluate parts of your functions and so forth. Okay, so what does the internal representation of this add look like? Well, here's the actual code for a double polymorphic function in Pixie. And As you can see, it looks a lot like Python, and we have things like dictionaries and lists. So a function in Pixie is simply a class that has a method called invoke, .invoke, and it takes a list of arguments. And what we're going to do is we get the type of the first argument and the type of the second argument, and then we look up the function we want to call based upon those two arguments, and then we call it. So if we look at the body of this get function, we see that what we're basically doing is two lookups. We look up in one hash map to find another hash map, and in that second one, we look up the function we want to execute. Pretty simple, right? This is a simple way to implement a polymorphic function like this, even if it is a little bit naive, right? But if we start to realize that we are executing this invoke for every single integer add in our language, how could this possibly ever be fast? We're doing two dictionary lookups for every single mathematical operation, plus boxing and a bunch of other stuff. So this is where a tracing JIT comes into play. A tracing JIT doesn't look at the code like we would expect, but instead looks at loops and uses loops to provide context. So here, what is the actual context of the code we're interested in? It's the body of this loop, the code between the top and the bottom of the loop. And within that loop, we have all the context we need to know the types. Now the problem is with tracing JITs, they're really, really hard to write. The original tech was written like all good tech sometime in the 70s. It was by HP, I believe, wrote the first tracing JIT, and it was a research project, you know. At one point, Mozilla had a JIT known as Trace Monkey that they discontinued because it was too hard to maintain. A little bit later, there was a JIT for Python known as Psycho, way back in the day. And it worked pretty well, worked great. One person understood it, and it was too hard to maintain and was discontinued. Let's see a bit of a theme here. One of the only existing tracing JITs outside of Python is actually Lua JIT, which kind of benefits from the fact that Lua is such a simple language that maintaining a complex JIT like this is not as hard. Well, the developers of PiPI had this great idea. They said, you know, we're already translating to C, and C doesn't have a garbage collector, but we're writing code that like layers the garbage collector into our Python code for us. Why not do that for a JIT? Why write a JIT that's hard to write? Why not make the computer do that? That sounds like a fantastic idea. So that's exactly what they did. They don't write JITs. Our PiPi-based languages, our Python-based languages don't write JITs. They write hints to a JIT generator that writes it for you. It's really crazy and fantastic. So a lot of that just mostly involves marking the start and the end of the loop. So inside the Pixie interpreter, we have certain hints that say, hey, here's the start of a loop, here's the end of a loop. And that code's a little complex, and we won't get a whole lot into that. But here's a simpler bit that I think we can all look at today. And that's this annotation at the top of this function called Eli Double Promote. And what Eli Double Promote says is that if this method is handed the same arguments over and over, you can replace the call to this method with its returned value. And we all know that as being pure. Like, why would I just mark this as a functionally pure method? Well, purity also means you're not doing side effects, and you're allowed to do side effects in here as long as they don't change the output. So things like caching and stuff like that are allowed. And so Eli Double Promote makes a little more sense. And if we look back up at our code here, we can see that that really helps us quite a lot. We say if we call add with two integers, then we can assume the function that we want to invoke in this lookup is always going to be the same. And if it's always going to be the same, we can look at that function and realize that it takes two ints and returns an int, which means we can basically type the entire body of this loop. And that's done for us by the JIT. So a tracing JIT is known as a tracing JIT because that's basically what it does. It'll find the loop and then walk the entire loop, recording every instruction executed by the interpreter and anything the interpreter calls, and create a long linear trace with all the branches removed, all of the conditional logic removed, and it's just one pass through the JIT. It will go back later and patch up branches if it needs to, but in general, it's just a linear trace. So here's what a trace looks like for that code that we looked at. And you know, kind of squint, it's a little hard to understand, but the blue bits here are basically the bytecodes executed by the Pixie interpreter. So, here we're inside equals, we're down here inside increment, and then we go into plus, and then we go back out of that into increment and so forth. And if we rip out all that debug information, here's what's left. For all those functions, all the polymorphic dispatch, everything, we have a label, we have a guard not invalidated, make sure no one has modified our polymorphic functions out from underneath us. We're going to do an integer comparison, we test whether it's true or false, and we do an add and check if we overflow and jump. All that gets compiled to about 4 CPU instructions. And that's kind of what originally excited me about writing a tracing JIT for a Lisp, was that in functional languages, we tend to write these really tiny functions that don't do a whole lot, or are just compositions of other functions. And a tracing JIT has the ability to dive through all of that, remove all of the niceties that we like to have, all the composition, and return a very nice, concise trace that's actually pretty fast. And so we can also do really crazy stuff like this. So we talked about before that a variable length function, a function that takes a variable number of arguments, in Pixie returns it as an array. So here we can just create this function I'm calling atom, we call it sum or whatever, that basically just takes all its arguments and adds them up. And we do that with reduce. So reduce, our accumulator is 0, add everything in using plus. And once again, so we're doing, there's a loop inside of reduce, there's a creation of array, argument arrays, and all this other stuff. And if we go through and look at this trace as well, it's a little longer. But basically, when we get all the way to the end here, this is the reduced trace. Once again, just a couple of additions. All the overhead of creating argument lists out of arrays and lists and all that is just removed for us. So that's cool. That was one of the first things I wanted to have in a language that I would write as a Lisp with a tracing JIT, because they really don't exist. There's a few languages out there that try this, but there haven't been a whole lot that have been attempted. So the second thing I always wanted to have in a language like this was lightweight threads. The ability to have threads decoupled from OS threads and to do things like a continuation from those. So thankfully, we sit on the RPython toolchain, which has some facilities for helping us do this. And let's see here, how about there we go. And what we can do is we provide this abstraction that I'm going to show here for creating lightweight threads. So we're going to create a promise, which is kind of a cell we can put things into. And then we're going to create this thing called a future, which creates a lightweight thread, which is just, if anyone here is familiar with like set, jump, long jump, and C, that's kind of what we're doing here. Some weird trickery with the C stack and that sort of thing, but in a way that doesn't mess up the JIT and stuff like that. So we can create this little lightweight process, and within the lightweight process, we can make this call to call CC. Now this is different than the scheme call CC in that it's not a full continuation of the entire program. It's just a continuation up to the start of the body of whatever process, lightweight thread you're in here. So we can get our continuation, and we get that as K, and we put that in the promise. So what we can do is run this, and we see this before call CC down here in our REPL. So at this point what's happened is this little future is executed up to the point of this call to call CC, and now we have a handle to the remainder of the execution of this process that we can go and wait to execute. And this is not any sort of macro magic or anything. This call to call CC could be 50 layers deep in a call stack somewhere, and we can just save off the thread and pause it. And we can print it here and see that the value is actually a stacklet handle. Okay. And then later on, we can come along and say, okay, let's continue on. And this is some weird machinery, mostly because this is often in library code somewhere. And when we run this machinery, it says call CC returned 42. So we passed 42 to the continuation. That then is put in as the return value to call CC, and this little process continues executing, and we see the output on the right side here. So what does that get us? Well, what we did in Pixie is we decided we needed a good I/O library, something that had some good abstractions. And so we pulled in the libuv library from Node.js. Node.js has a nice I/O library underneath called libuv. And if anyone's ever programmed in Node, they know that it's callbacks everywhere. But if at any time you can take your currently executing thread and turn it into a callback, then you can take and create these little lightweight threads, and at any time just pause them, attach them as a callback, and continue on. So in our example of our Mandelbrot code, we do that here at the end. We just call sleep for 10,000 milliseconds, or 10 seconds, and that executes this code here. We call cc to get our continuation, hand that continuation off to libuv and say, when you're done, call us and we'll continue on. So that's kind of cool. The ability to do this I/O, this asynchronous I/O, and work with libuv in a way that is nice for the programmer and not just nice for the runtime. And on top of that, we can build all sorts of things. So here's an example of a communicating sequential processes code, a lot like you would see in Go, or for instance, core.async and Clojure. But in this case, we're not using macro magic or syntax or any sort of compiler thing. Our put and take from channels, the ability to pause the current thread as we're giving values to another thread, is just a function that we pass around. And with this sort of these stacklets or these continuations, we can do all sorts of things like build generators. You can do some complex like exception handling or just asynchronous operations. Okay, so let's see here. I want to talk a little bit about, I will talk a little bit about this here because it's a kind of cool example. Another thing we added to Pixie is a really simple open-ended object system. So, and we'll see an example of this used a little bit later. But we have these dot forms. If you're familiar with Clojure, this is a type of way of doing interop, saying on this object, pass it a message, which is a method I want to execute on that object. A lot of languages have this. Python has get attribute. Ruby has something like that too. I forget the name of it. But we have that sort of thing in Pixie too. So it's an open-ended object-oriented system. So we can define an object, and then we can, in this case, say if we try to look up attribute X, then we're going to return a value, otherwise return not found. So here if we look up X on this object, we get 42, and if we try to look up Y, we see it's not found. And we'll see a cool use case for that in just a few moments. And same sort of thing with methods. Okay, so the two things so far we discussed is tracing JITs and these stacklet features, which are kind of nice. The third thing I really wanted in a Lisp was good, rock-solid foreign function interfacing with C. This is something I haven't seen a lot of languages do because it tends to be fairly hard. Now, the RPython toolchain provides good functionality for calling C functions in the sense that you can say, here's a pointer to a C function, and it expects a double and returns a double. And once you call that a bunch of times within a trace, it will compile down to just a call to a pointer. So all the logic of wrapping and unwrapping and all that is pretty much removed, which is nice. But you still have that problem of what are the types of this function pointer I am calling? And that tends to be a pretty hard problem. So the holy grail that I was looking for, the thing I really wanted to build, was a system where I could say in Pixie, from math.h, import cosign, which is a pretty tall order because there's a problem, and that is so there's a library in libc called M, and if you go to this library M, you can look up the symbol cosign, which just gives you the pointer to a function. That's it. You don't know what that function expects, you don't know what it returns, there's not a whole lot you can do. Because all of that information, all the typing information is stored in the header file math.h. So different libraries out there approach this sort of thing in different ways. There's one approach is to do what the JNA library does for Java and just say, well, you better not hand me the wrong arguments or we'll segfault the whole the JVM. Okay, that works, but you know, it's not optimal. And it requires people to add their own asserts and type checks and everything. Another option is to do what CFFI does in Python and say, well, hand me small snippets of C code that define your functions, and I have a C parser, and I'll go parse those and use that. That works as well, but you know, no offense to anyone here, I don't trust any of us to write a C parser. You know, it's a really complex beast. There's a lot of weird macro magic, and it never really works out well. Probably at this point, a lot of people are thinking, well, hey, didn't LLVM build a library that's a C compiler? Yeah, they did. It's called clang, and then they wrap it up as a library called libclang, and that works pretty well, except it's like 30 meg. And the last thing I really wanted to do was to have, Pixie, this light, fast language with this huge C compiler bolted on, So I actually thought about this quite a lot and finally came across an idea, which was to use or abuse, however you want to look at it, the Boosttype traits library. So in modern versions of C++, you have a way to conditionally execute C++ templates, and we leverage that extensively. So here is a template that only compiles when the function handed to the template is a function that has one argument. And we have multiple instances of these. So it's just a cascading list of templates. Each one fails if you hand it the wrong type. And eventually it'll find the right template to compile. So in this case, you handed a type of a function that takes one argument and returns something. And then we recursively call that template to do reflection upon all of the arguments and the return type. So we have this library called FFI infer, and it looks something like this. And this is pretty much what I was originally looking for. We say there is a dynamic library on the system called M. If you're going to execute a static link against this, you need to link against it using libm. Okay, this is pretty simple stuff. And all of the header information, all the information about the functions I want to execute is found in math.h. Great. And then you just start listing off symbols that you want to import using that specification. And what this library does behind the scenes is take all these symbols, create a C file with all of these things plugged into that template, compile the file, and then run it, and that spits out all the type information. So we can do that here. It takes just about that long to compile and run on this system, which is pretty fast. And now we have floor, cosign, and sine, just as normal Pixie functions in our language. Oh, thanks. And one of the cool things that we built in Pixie is an ability to output bytecode as a file on disk. So all of, this is a macro, and if you have a lot of imports, this will take a while to compile. It may take 5-10 seconds or something to compile all those templates because they're not exactly fast. But when we're done, we can take the bytecode generated by this macro and spit it out to disk so that next time you come to run this module, it loads almost instantaneously. And the takeaway from that is you only have to have Boost and C compilers and all that other junk installed on the development machine. You wouldn't have to have it on a production machine. But don't use this in production yet. And we can do this for all sorts of stuff. So for instance, here we have a C struct. This is from the libuv library. And we can say import the C struct. And here are the members I'm interested in. This will go find out their type, their offset, their size, everything it needs to know, the size of the struct. So you can just instantiate this struct, set the members on it with any Pixie values that are compatible, and you're off. You can also import compile time constants. So like if this is, UVFS link is defined as 42, we can import that as well. The really crazy thing we can do is import C callback types. So this is a callback type from libuv. And if you want to talk to an asynchronous function in libuv, you have to hand it a C callback. So the first thing you do is import the callback in this fashion here. And then you go and do something like we had up here. And let's see here. Here we go. And I'm running off the edge of the screen a little bit. But there's this function called FFI prep callback. And you hand it a C callback type and any Pixie function. And it coerces that function into a C pointer that you can hand off to C. So what this means is that you can kind of just interop between C and Pixie. You take a function, hand it to C. If C hands you a function, you can cast it to one of these types and call it. It's just very, very easy to talk to C in that way, which is cool. So I was talking about this once, and an acquaintance of mine said, well, you know, Python has a really cool C API, doesn't it? Well, yeah, it does. And you say that you can work with cool C APIs pretty easily, yeah? So why don't you call Python from Pixie? Okay, let's try it, you know? You can actually do it. It's actually really weird. So this here is compiling all the type information it needs to talk to Python. And so here is a Pixie function that creates a vector. And this calls the Python code to create a Python list. You can see it's different because it has commas. You know, the type is this wrapped py list. And then we can do cool things like call count on it. So this is Pixie's count function that has been extended to work with this Python list. And then we can do something completely crazy and hook into that open-ended object-oriented dispatch thing I talked about earlier to say that when an arbitrary Python object is called with, you know, a .append is called on it, go look up that method in Python, turn it into something I can call it handing it the arguments, and give me whatever it returns. So what we're doing here is creating a Python list, adding an integer to it, and returning that list. And we see, in fact, we get 1, 2, 3, and 42. So I'm not exactly sure how useful this is, but it's a cool exercise nonetheless. So one thing I did want to point out here, though, too, is let's go look at this Mandelbrot code again. So at the top, we kind of see all of this come together in this example that I showed earlier. This is all it. So I'm doing interop with STL, which is a nice cross-platform graphics library for C. And so we're just basically saying, you know, we're going to link against STL2, and here's where we get the flags on how to link to it. We're shelling out to a shell script. We're including stl.h, and from that, I just need these functions. So there really isn't an STL wrapper for Pixie at all, because you don't really need it. It's just these, you know, 10 lines of code. And from there, we just call the functions as if they were normal functions. And we have some interop here for packing data into an array, which we then hand off to STL as the frame buffer. And this is the guts of what we showed with the Mandelbrot code. It's just loops and normal Lisp code. So actually, that's pretty much all the things I wanted to go over today with this. It's a fun project. You know, it's with being built on top of RPython. It's pretty easy to get into and play around with, and we have people stop by all the time. There's about 3 or 4 committers that help me with this on a regular basis. So the link up here is at the top, github.com, Pixie Lang, and it's just download it, try it out. Let me know what you think. It's fun to play around with, fun to just you know, tune the JIT a little bit or look at something that interests you. And I guess I'm a little early today, so that's all I had. Thank you, and I guess I have questions, or you might have questions.